Okay, here's our DC motor once again, and I want to remind you of all the key components in the DC motor. An axle that it rotates on, brushes to lead the electrical current into the commutator, and then these coils act as the external magnets, and then the external magnets exert not just a force but a torque on this current loop, and then we get to spin around. In other words, electrical energy comes in and we get mechanical energy out. Well, now what you're looking at is a generator, and a generator really has all the same parts as a motor. The generator just reverses the transformation of energy. Instead of putting electrical energy in to get mechanical energy out, we're going to put mechanical energy in by cranking with our hand, and hopefully that creates a voltage output. So I have wires to register whether or not there's a induced EMF across the terminals of my output. In fact, I even have a galvanometer that'll tell me if there's any output at all. All right? Let's hold off on hooking up this galvanometer for a moment and look at all the key parts. Well, this is definitely mounted on an axle, and look, we've got a coil of wire that spins, and it spins in the presence of some external magnets, and there are brushes that take the electricity off of a commutator. So, in fact, I should be able to connect a DC power supply across here, and when I do, this thing would start to spin. It would act like a motor. But we're going to use it as a generator in this case. I better verify that the magnetism is aligned, right? So I've got my paper clip. Let's see. Yeah. Back here. Yeah. Now, here's what I want to check. Oh, goodness. Do these two magnets attract or repel each other right now? Oh, they're repelling each other. I can't get them together. If I turn them this way, they attract. So when I put them on here, what I've created is a magnetic field. And at this moment, the magnetic field lines are passing through the area, the cross-sectional area of this loop of wire. And so I have maximum flux right now. Right? Flux is the dot product between area and field. And right now, the angle between the normal vector to this loop and the magnetic field lines is 0. So if we say magnetic flux is B, the magnetic field strength, times A, the area of the loop, times cosine theta, this is a case where theta is 0. I've got maximum flux right now. If I turn it to this orientation, I got 0 flux right now. And if it's at like a 45-degree angle, there's a partial amount of flux. So as I crank this, the flux is always changing. Not because I'm changing the magnitude of B or changing the magnitude of A, what I'm doing is changing the value of theta, okay? So the faster I crank it, the more voltage I should get, and let's just see if that's revealed on our galvanometer. So the needle is clearly on 0 when there's nothing. Now, if I turn it to here, again, now I've got flux. The needle doesn't register, but then again, that's the whole idea. Flux itself doesn't make voltage, it's the rate of change of flux. So it's only while this thing is spinning and the flux is changing that I have any voltage. Notice the needle always moves in one direction. I was just producing DC. Now there's another way to do this. Instead of using a commutator that has a gap, I can make 2 separate rings, one brush that touches this ring all the time without a gap in it, and then this brush that touches the other ring. And now in this case, notice what happens on my meter. It swings to the left, it swings to the right, it swings to the left, it swings to the right. We're producing an AC output voltage. It just depends on the brush and commutator arrangement. So there it is. Generators convert mechanical energy in to electrical energy out, whereas motors put electrical energy in to get mechanical energy out.